Hello and welcome to this edition of our global webinar series. Today's topic is choosing the right supercapacitor. My name is Alexander Nebel. I am Field Application Engineer in Europe and I will moderate the webinar today. We are very pleased that you find the time to join our webinar. Presenter today is Roya Nikjoo, our Field Application Engineer in Europe. With this information, I hand over to Roya. Hello, Roya. Thank you for presenting today. Please tell us a little bit about yourself before you begin your webinar.
Hello, Alex, and everybody. Thanks for the introduction. Today, we're going to talk about choosing the right supercapacitors for different applications. My name is Roya Nikjoo. I'm a field application engineering for KEMET in KEMET Europe, responsible for the Nordics and Baltics. I joined KEMET more than 1.5 years ago. I took a PhD from KTH in Stockholm in electrical engineering, and also had a postdoc as a research fellow at University of Bologna for a while. And also, before joining KEMET, I worked as an application engineer at an electronic test equipment manufacturer. And before that, also as a design engineer before my study at KTH. But also, I worked more than this that I have written, but I do not want to make a long list. You can see my email and my mobile phone number in case you have questions. I would be really happy to answer your questions later. Today we're going through the different topics regarding the supercaps. First, we're going through what are the difference between supercapacitors and the batteries. How does the supercap work? What are the structures and different types of supercaps? What are the KEMET lineup series? Application examples, and also how to calculate the correct capacitance for your applications, and later also talking about the parasitic effects that are important when it comes to the supercaps, competitive advantage of the KEMET products, and also mentioning about the automotive grade supercap that we can offer. And then we have a summary and a recap. So when it comes to the supercapacitors, also we might think about the coil cell batteries or the batteries as well. What are the benefits or the pros and cons when it compares to those, and where we can go for the supercaps? When it comes to the principle of electric storage for the supercaps, they have a physical absorption of, and their construction is based on the physical absorption of ions. But with the lithium coil cells, it's like a chemical reactions. When I call secondary battery, primary batteries are those batteries that can be used only once, and then you cannot just recharge them. But the secondary battery are those that you can also charge and recharge like several times, and it's not only limited to once. So mostly maybe it's a comparison of these two. When it comes to the failure mode, the supercaps will get open in a kind of a failure. So compared to the lithium coil cells, which they get shorted, it has a benefit. They get, like in the case of like a failure, the lithium coils, they will have outgassing, ignition, and rupture, but this won't happen for the supercapacitors. When it comes to this charge and discharging cycles, like the lithium coil cells, they can have up to approximately 500 cycles, but for the supercap, we have no limitation. So they can be charged and discharged as many times as possible. So they don't have a limitation regarding those. When it comes to the charging time, it is also another thing which makes them popular for some application is like several seconds, because they have a quite low resistance compared to the lithium coil cells, which have a high resistance. For them, it can take for the charging time like 10 minutes or several hours, but the supercapacitors are really fast when it comes to the charging time. When it comes to the energy density, of course, they don't have as higher energy density as the lithium coil cells. They have a lower. But of course, when it comes to this point, we can say like the lithium coil cells, those have a high energy densities, but supercapacitors, they have a high power density. I mean that you can get so much energy in a very short time. But for the lithium coil cells, those can like store more energy inside compared to the supercaps. Regarding the operational temperature for the supercaps, can have it from -40 to 85 degrees. But for lithium coil cells, it's more limited, like from -20 to 60 degrees. And another important advantage of the supercaps compared to the lithium coil cells are the maintenance. They are maintenance free, so they don't need to be go through any maintenances. But the lithium coil cells, yeah, or they must be replaced. So these are the advantages that we see. But of course, like the applications that the supercaps can be used in, maybe compared to lithium coil cells, also different or limited. So how does the supercap work? We call it like an electrical double layer capacitors. In the construction of this type of supercap, we use the solid carbon electrodes like these A and B that you can see toward a liquid electrolytes. So in the principle is actually the charges that are inside the electrolyte when we apply the voltage, so the like the opposite ions get attracted to the opposite polarity of the electrode that we have, and generate a very thin separation distance between the charges. And this separation distance is very thin, like around 1 nanometer, which also leads to the very high capacitance. But of course, another parameter is the porous property of these carbon electrolytes, that these ions penetrate to, and through the absorption and desorption of that, it generates actually these layers, and that one also causes a high surface area. So we increase the surface area through the carbon property that we have, and a lot of porous, and that which causes a high surface, and also this very thin layer that form between the ions, which we call it inner Helmholtz layer, provides a very thin or a small d. So as you can see here, both this A and D, the increase of A and decrease of D, helps us to have a very large capacitances. As a result, so we have a 2 double layers, as you can see here, as in series, creating physical charge separation, and electrical charges have been stored in this double layer. We have also the mechanical separator, which is like a film layer, which helps to do the isolation act, and in case of failure, it won't let the 2 electrodes to attach, but at the same time lets the ions to move around easily. So we have different supercapacitor constructions. Maybe we can categorize the 2 major and more popular types to aqueous electrolyte and the organic type electrolytes. KEMET has the aqueous electrolyte structures for the supercapacitors, and some other competitors, they use the organic electrolyte type. So there are different insulation material, as you can see inside. But we have also, when it comes, different types of the, when it comes to the shapes and the mounting, can type, resin mold, or SMD types available. So when it comes to what are the benefits in our design, when it comes to the KEMETS supercapacitors, we have actually providing high reliability design. One of them is due to the way that we use the termination and the cross-linking for the terminal, but it actually helps and causes made from the chemical bond near hermetic, which help us to have a longer operational life and a strong shock resistance. But compared to our competitor, which they use the gaskets type, so for the mechanical compressor, so they have a risk of leaks of electrolytes, what we don't have in our design. And of course, in using the gasket type, you can have like internal short or failure, or the big shock resistance. Also, you have this type of design, which we avoided in our cross-linking construction. But also because we are using aqueous electrolyte, we have a high reliability for moisture or high humid environment compared to the organic one, which is quite weak for the moisture. But of course, like the aqueous one has much higher conductivity also compared to the organic type, which also lower the ESR as well. And of course, and also it has a cheaper it also affects the price as well, beside the performance. Another advantage, or for high reliability design, that we have an advantage of the KEMET supercapacitors compared to competitive, is that we have a higher voltage margin in our design. So as you can see here, we compare the two 5.5 volt supercaps. As you can see here, this is like a can type or the cold type. And for us, it's like a cell, we use a cell stack. We use, like, for example, here, as you can see, it's like 6 different cells that are used. Each cell is the maximum voltage of that is designed to be 1.2 volts per cell. But we actually considering the 5.5 volt, each cell will be exposed, or 0.917 volt is applied to each cell. But when in the competitive one, when you use just 2 cells, and then they will have 2.75 volt per cell, and the maximum voltage of base cell is 3 volt. So what makes it the difference is that in our design, we give like much higher voltage margin. Like in this design, you can see it's a 30% margin, while for the competitive part, they leave only 8% margin. So when we have less voltage stresses, we can avoid a failure. So voltage stress causes the electrolyte to break down and reduce the life of the supercapacitors. When we when in our design is actually we have the higher voltage margin, and it helps us to increase the life of the capacitor and reduce the cause of the failure and the breakdown of the electrolyte and the breakdown. So when it comes to the KEMET lineup and focus series, we have different mounting type, and as we can consider, like the surface mount type, we have resin molded through hole ones, and also the can type. So it depends on what are the mounting type you are looking for. You can also consider different series. But of course, in different series also have different capacitance range and voltage ranges and maximum temperature ranges. So based on that, also you need to look for a specific series that according to your specific application, capacitance, voltage, and temperature. Series that actually we offer with the temperature range from -40 to 85 are these series FTFR, FM, FMRF, and FGR. When it comes to the performance for selection, so we know that like one of the most important things, we want to choose the right capacitors and right series for your application. So when it comes to that, like this graph is one of the basic one that can help you to look through which series you need to look for. If you're looking for the higher backup time, like as you can see here from 1 hour to even 1 month, you need to look for the high impedance application use series, which are listed here. But if you are looking for the shorter backup time, you go for the low impedance application use, as the series are mentioned here. And of course, if the application is for high power one, you go for the HV series. But as you can see here also, like what will be the backup current depends on the supercapacitor series as well, so which is affected by the impedance of the supercap. Another table that we have that can actually help you also with more information regarding the backup time and application and the relevant series as you can see in this table. For example, according to if you are looking for the long time backup, and also like the current from 500 microamp and below, for the application such as CMOS, RAM, IC for the clocks, microcomputers, and the equipment like measuring devices and those, so these series can be useful. For example, specifically if you're looking for the 85 one, so better to go for the FR series, and the other ones are for the other temperature range, even though we have also for FM series the 85 degree. When it comes to the backup time for 1 hour or less, 550 milliamp and below, so we have other applications, microcomputers, driving motors, and it can be like micro ovens, it can be printer, camera. So these are the series that can be suitable for this type of application and this backup time. When it comes to backup time for the 10 second or less, 1 amp and below, so there are other applications like power source of toys, LEDs, buzzer. So these series are suitable. And for the power assist power supplies, we go for the HV series. So this is also another table that can help you to look for the right series for your application. So we have a different application examples, as we already listed some, and also some examples of the part numbers which are relevant to from utility meters, automotive, infotainments, flight entertainment, base station for communications, digital camera and digital network, industrial robots, and other applications such as installing pumps, ultrasonic diagnostic equipment, and so. And also we have provided some sample or examples of the part numbers and the series which are useful. And for many of them is actually using also for the RTC application, real-time clock applications. So the next step and the most important one is actually how to calculate the correct capacitance for your application. So you already looked through your application and through the tables and the graphs that it provided, somehow like which series can be used for your application. But then you need to also know which capacitance you need to choose, and that would be right for your application. So for your application, you have these following parameters. So one, required backup time is one of the important parameters that you actually want to satisfy. Then you have a required backup current, minimum and maximum operating voltage, and of course other parameters such as operating ambient temperature, required dimension and mounting type. So these actually affects also the series that you're looking for. But from these parameters that you already provided here, you can roughly calculate the capacitance which is needed. So you need to multiply the required backup time to the backup current, and then divide it by the difference of the maximum and minimum operating voltage. This gives you a rough estimation of the capacitance that you need. But we don't have only, there are other parasitic effects that you need to consider when you're calculating the capacitance for your supercap. One of the parasitic effects that you need to consider is the R series or series DC resistance. This is the resistance of the capacitors, terminal and electrode, and also ohmic losses within the capacitors during the movement of the charge carriers. And actually the multiplication of these resistance and the capacitance value impacts the charge and discharging time. Because of that, it is one of also important parasitic effect that you need to consider when you are calculating the right capacitors for your application. ESR is considered as an AC resistance, which is also frequency dependent. So the DC resistance is the resistance that you see at the low frequency region. So we usually provide the ESR at 1 kilohertz in a spec sheets, but you need also to look for the DC resistance or series resistance in the data sheet for this value, because for your calculations of the capacitance you need to consider this value. But as you see, like the whole ESR is also frequency dependent and also temperature dependent, the same as with the capacitor. So you need to consider like that as well. So in additional parameter that is needed for this the calculation, we said that it is the R series or DC resistance, which actually caused the voltage drop over the capacitor. So the voltage drop of the supercap is determined by the DC resistance and the backup current. So to calculate this voltage drop, you need to take out this DC resistance from our data sheet and then multiply it to the backup current. So in order to have a more accurate estimation for the capacitance that you need, you also need to calculate the voltage drop that we have over this DC resistance of the supercap as well. So we complete the previous formula with the voltage that we have here, also reducing the V drop as well. So another parasitic effects that also come and plays a role in your decisions for choosing the supercapacitor is the self-discharge characteristic. So self-discharge characteristic is measured when the main charging source is disconnected from the supercap. So it's in the discharging situation. So we usually provide you also for the different capacitors and part numbers with the self-discharging capacitors. And it is important to determine the backup time and needs to be taken into the consideration. And as you can see here, different value can have different self-discharging characteristic. It means that also the voltage that drops by time when you start discharging. But of course, this characteristic is also defined at a specific temperature, and we charge at the usually the maximum operating voltage of the supercap and for a specific hour. This hour is also effective and important in the self-discharging characteristic. So usually KEMETS, when we provide these graphs, we define it as a 25 degrees and also the charging time is 24 hours. But this self-discharging characteristic is also temperature dependent. It means that at higher temperature, you will have a higher self-discharging current or even a more loss in the voltage when it comes to the self-discharging characteristics. So this is additional parameters that we need to consider when we do the calculation, especially for the backup time. Before we already could calculate the capacitance, so we get the graph of the self-discharging capacitor from us. And now you want to calculate what is the actual backup time considering the self-discharging characteristics. Regarding the V drop that I said from the DC resistance, just to mention also that when the backup current is 1 amp or below 1 milliamp, below 1 milliamp, we usually neglect the V drop. So we can consider this 0. So usually for the RTC backup applications, we consider this one negligible. But anyway, when we want to calculate the self-discharge current from this graph that we have, we have that a specific capacitance value we calculated before, and we chose this graph. So, and we consider 2 points, 2 different voltage, V0 and V1, and then we check what will be the time between this in the discharging time. This is what it is here. So we multiply the capacitance to the difference of the voltage level. And if we have V drop also, we consider the V drop as well. And over this discharge time for these 2 points that we chosen on the graph. So this gives us the self-discharging current. And through this, when we want to, again, estimate the right backup time for this capacitor, we calculate in our calculation, we consider Vmax and mean of the operating V drop. And here also we add the self-discharging current to the backup current as well. So this also affects that you will get the smaller backup time compared to what you previously estimated. So through this you can see if it is still in the margin that you want, or you need to go and choose another capacitance value. When it comes to the parasitic effect, we have also another thing, we call it leakage current. But just to mention that most of the cases when you are reading about the supercaps, you see that this self-discharge current is the same as leakage current, but it's not exactly the same. Leakage current is the charge current measured from the pin-to-pin voltage across the charge resistor when the supercap is charged for many hours and while the supercap is uncharged. While the self-discharging current is in a situation where the capacitor is getting discharged. So it might be similar like in the value, but it's not exactly the same. So this is another thing that usually like also people look for. What is the leakage current of the supercap? When you are charging at the beginning, like the charging current will be high because like a lot of ions want to get absorbed inside the pores of the carbon, and so we have kind of a high current and we call it absorption current. But after a while, when the capacitance gets charged, this current gets to kind of a steady state condition, which this current we call it leakage current. But it's also different values of the capacitors, and also this leakage current is affected by the temperature as well. So if you need to see what is this leakage current, and it's one of the criteria for your application, you need also to check what is your operating temperature and what will be the leakage current and that specific temperature. So another things in parameter which is important to look for is the ambient temperature, because the operation temperature is one of the main factors for choosing the right supercaps, because the temperature can affect lifetime of supercaps, self-discharge characteristic or discharge time of the supercaps. It affects the leakage current, it affects the capacitance and also the DC resistance. As you can see here, this is a graph for how the capacitance the value of the capacitance can change by the temperature. So this is also important things to look for, and look how much would be the variation of the different parameters regarding your operating temperature. When it comes to the lifetime of the supercapacitors, so we define the end of life for the supercap when their capacitance value is reduced to 70% of initial value. So when you have the life temperature load life test, the life is reduced by half with an increase of 10-degree temperature. If you look at it like for one of our FC series, for some values you can see here, when we are decreasing like 10 degrees, the temperature, the life also decreases by half, because the acceleration coefficient is 2 power t minus t0, as you can see here, over tau, which tau is like 10 for 25 to 70 degrees. When it goes to the higher temperature, 70 to 85, this is 7. So it means that you will have a sharper like a line here when it comes to the higher temperature from 70 to 85. But as you can see here, but if the lifetime of supercaps is considered like around 10 years at the ambient temperature of 25, as you can see here at 25. And then if your temperature would be higher, so you need to consider it can be a lower lifetime. So in many cases, you need to probably, if you want to use it for a high temperature, you need to cool it down in some way to reduce the ambient temperature to increase the lifetime of the supercap. But of course, for very high temperature applications, maybe you need to go through the lithium battery cells instead of the supercaps. But when it comes to ESR, as also maybe I mentioned a little bit regarding that, the KEMETS supercapacitors are having quite low ESR compared to our competitors, because it's also aqueous, and aqueous type having higher conductivity and also having providing a lower ESR. And as you can see here, compared to our competitors, especially at lower temperature, is quite stable, and from low to high temperature is quite stable with the temperature. So the KEMET products having better ESR stability over the temperature. When it comes to high temperature and high humidity tests, with the test, this is that there are the results that we have provided from the test condition of 85% humidity with no load up to 240 hours. As you can see here from the capacitance changing rate, maybe there's not so much difference between the KEMET and competitor products, and also from the leakage current, KEMET product is lower a bit, but not a huge difference with the competitor. But when it comes to ESR changing rate and also the self-discharge characteristic, you can see here like the ESR by the time is so stable, it hasn't increased much, but in the competitor's product, ESR has changed a lot and increased by time. And self-discharge characteristic the same. We have a less voltage drop over the KEMET capacitors up to 240 hours in this test condition. And for the competitor's product, we have much more voltage loss and self-discharging characteristics by the time with this test condition. So KEMET products have a quite much better ESR and self-discharging performance compared to our competitors. When it comes to the new supercapacitors that we have, actually we have the ACQ 200 compliant product that we are introducing to the market. It uses the aluminum capacitors as standard for most passenger compartments and the temperature range of -40 to 85 degrees. So it is a mold type FM series, and it starts to have a mass production at the beginning of the next year. So what we went through regarding the supercaps, they have no limit for charge and discharging cycle. They are so quick in charge and discharging because there is no chemical charge involved. It has an open failure mode, simple in installation. We have SMD and automatic mounting series available, also like through-hole one. Wide operating temperature up to 85 degrees, high reliability in humid environments, as I mentioned, because we have also a special design. It is maintenance free, and every application that needs a small power backup solution is a potential for supercaps. But always keep in mind, supercaps are having high power densities, while the batteries, they have high energy densities. So thank you for your time. I'm open for your questions.
Yes, thank you, Roya, for presenting. We received some questions, so I will hope you have time for all of them, but still to the audience, if you still have questions, please ask them, and if we don't have enough time, we will answer them later. So the first question is regarding slide number 8. What happens to the supercapacitor performance or failure mode when the electrolyte breaks down due to voltage stress?
As we mentioned that the supercapacitor failure mode is open mode. So even if we have the electrolyte breakdown due to the voltage stress, as of course you mentioned that even the KEMET supercaps have a higher margins, but it's still like in case that you run it much higher than the limit, and even considering our margin, you will have a failure, it will be an open mode. So it won't be shorted because we have the insulation layer between the electrodes, so they never get shorted.
Okay, the next question. What type of electrolyte do you use to obtain a supercapacitor with a working voltage of 5.5 volts?
Those ones that are almost all our KEMET products, we use the Aqueous electrolytes type. So if it doesn't matter, even for the 5.5 volt, it is the same. It's not different between different voltage levels.
Okay. The next question, what maximum voltage would an HV capacitor be derated to if using at 85 degrees centigrade? So
the thing is that maximum voltage, so usually we say that the voltage that is defined for the supercapacitor is the voltage, like the maximum that is mentioned, it is actually the one that you can operate it at that voltage level. But, and also when we define the temperature, it means that we don't want you to operate it at this higher temperature. But if you, because the voltage is even more severe. I mean, if we say this voltage, you shouldn't run it above that voltage. Above that 85 degree, maybe for a very short times, various one, not always, can work, but you need to consider that it can affect the lifetime of your capacitors. So that is one of the things that we usually tell the customers.
Okay, so I still see some more questions. The next one, I don't know exactly to which slide number it's related. Why does the TAO change and drop more at higher temperatures?
Sorry, what are...
It's, I guess it's to running calculation, to your calculation. Why does the TAO change and drop more at higher temperatures? So maybe I'm not sure about this, so we can maybe answer this question later. Also, the rest of the questions, because we are also running a little bit out of time, are very specific. We will come back to you later. So because there are some special information needed to come back. Because for this moment, I can see these are all questions which can be answered directly. And to the rest, we will come back later. So for the moment being, Roya, thank you for presenting. Thank you for this interesting presentation. To all of the attendees, we will publish the presentation and the recording later on, also the open questions. And with this,
sure, yeah, I can answer the questions after the presentation.
Yeah, sure. So and with this, I want to say thank you, and I hope to see you soon again.
Sure, thank you. Thanks.
Say goodbye.
Bye.